Let me just review a few of the things that we got into last time, which was a week ago. We talked about, first of all, density, the idea of mass per unit volume. So the more mass is in a smaller volume, the more dense a substance is. Same volume, heavier objects that have the same volume will have a greater density. Most people have pretty good intuition about that. Less good intuition and more important in this chapter is the idea of pressure. And so we've been developing some ideas of pressure in a fluid. Fluids generically are either gases or liquids. Those are the most straightforward kinds of fluids. There are lots of things like jello and mud and things like that. They're sort of fluid-like, but not so fluid-like. We're going to stay away from those confusing boundary cases. So liquids or gases. So here are some properties of pressure in fluids that we sort of briefly proved. You don't need a solid surface in order for pressure to be defined. So we defined pressure to be the force due to a fluid, and it's generally due to those molecules hammering against the edge. You know, if you think of a cylinder of water like this, right? There's thermal motion down at the molecular level, and those water molecules are hammering against the inside of this. And we define pressure to be, take a little tiny bit of surface area and calculate the force due to that hammering on the surface and divide by the area, and the force divided by the area is equal to the pressure. Or we'll be using a lot that the force can be calculated as pressure times area. You'll see that coming up. Now, I was just speaking of it as if the pressure had to be on some solid surface, but you don't need a solid surface for the pressure to be defined. Right in the middle of the fluid, the pressure is perfectly well defined. And one way to at least make that make sense to yourself is you can think of one, dividing up two regions of fluid, and one side of the fluid is hammering on the side of it next to it, and that one's hammering on the side to its side too. So there's pressure all the way through the surface. And you can think of, the left half of a piece of fluid is sort of contained by the fluid on the right side and vice versa. It's almost like a boundary. It's just not a solid boundary. Another important property, if the fluid's in static equilibrium, that means it's not flowing. And in almost everything we're going to do in this chapter, there's a bit of more discussion of flow at the end of the chapter that we're going to skip just because time is short. But for fluids in static equilibrium, that means no macroscopic flow. There's always movement down at the molecular scale. We're not talking about that. We're talking about large volumes of fluid moving, some stirring motion or something like that. If that's not happening, then the pressure is independent of surface orientation. In other words, if I take a little a glass slide and put it under the fluid and I reorient it in different directions, the force due to the fluid on the surface of that glass slide is going to be independent of how I orient it. That's not at all obvious. The force is a vector quantity. It turns out the magnitude of that force is independent of the orientation, as long as you keep the location in the fluid the same. If you make it down at a deeper location in the fluid, we'll find out that the pressure does change from position to position, but the orientation doesn't matter. Also, if you have pressure on a surface, it's always in the direction perpendicular to the surface. The idea there is if the fluid is pushing on the surface like this, the surface pushes back at the fluid, and the fluid also has more pressure from the other fluid at its back, and it's not going to go anywhere. But if the fluid is pushing up on the surface is going to be pushing down on the fluid, and the fluid is going to start to flow down at the surface of the fluid. There's nothing wrong with that. That's what happens if I take this fluid and stir it. So it's moving against the surface. It's sort of trying to drag the surface along that way. And that means the surface trying to pull it in the opposite direction, which is slowing it down. That's why when you stir things, it slowly slows down, like the surface is trying to get it to come to rest with respect to it. But that's not a case, again, of static equilibrium. If the fluid's just sitting there at the macroscopic scale, the pressure is always in the direction. So in the inside of this, the fluid pressure is going to be perpendicular to the surface, always completely perpendicular, never any component parallel to the surface. Okay, so we did those a week ago. And the last one tells us that the pressure actually increases with depth in the fluid. I don't know why traditionally people use the symbol H, but the H is supposed to be how much you go down in depth in the fluid. I guess H for height, but you're actually increasing your depth in this case. It says the increase beyond atmospheric pressure at a depth H in the fluid. And here we're considering a fluid of nearly constant density, rho. Remember, our atmosphere is a fluid. And as you go up really high in the atmosphere, the density gets quite a bit less, right? And as you go out into space, the density approaches zero. But for water, water is a fairly incompressible fluid, and that's going to be our generic kind of fluid that we'll consider. The density doesn't increase much, even if you increase the pressure by huge amounts. So if you go down to the bottom of the ocean, the density of water compresses a little bit, so the same mass fits in a slightly smaller volume, but it doesn't compress too much. Really, those water molecules are right bunched up against each other, and there's not much room for them to get compressed even more. And so water is a fluid of nearly constant density, and so this is certainly applicable to water. It says that if you know the rho of your fluid, and one of the things we talked about was in SI units, rho of water is 1,000 kilograms per cubic meter. Then the change in pressure as you go down by a distance h is equal to rho gh. Okay, let's try to justify that with a little calculation here. Here is a rectangular, sort of cube or rectangular box of water. It's got an area A on the top and bottom, and it's of height h, like this. And one way to do it is to actually place the top of this actually at the surface of the fluid. I'm going to imagine this is water, but it could be any fluid, as long as the density is constant over this distance here. And what we're going to do is do a free body diagram for this rectangular box of fluid and draw all the forces that are acting on it. And of course, one force that's acting on it is the weight, gravitational force on it. And I told you to remember in the very beginning of this chapter that you would see a quantity that looks like rho GV appearing over and over again. And remember, density is mass per unit volume. So density times volume gives a mass, and m times little g is a gravitational force. So when you see a rho GV, this is a weight force. Okay, it's sort of unfamiliar collection of symbols, but it represents a weight. So the mass of this rectangular box times little g is rho times v, that's the mass. V is A times H, right? The cross-sectional area times the height gives me the volume of the box. So this is another way of writing rho mg, okay? There's also some other forces on this. There's forces on each of the 6 sides. Now, because the pressure on each of the sides only increases with depth as we go down here, we've got a certain pressure force that's sort of smaller at the top and larger at the bottom that's going to be equal and opposite to pressure forces that are smaller at the top and larger at the bottom. So the left and right-hand side forces cancel out on this cube. The front and back ones also similarly cancel out, because even though those little forces are getting bigger as you go down, they cancel out pair by pair in equal and opposite ways. But the top and the bottom aren't going to cancel out in the same way, because the pressure is less at the top, or at least we're presuming that it might be different here, okay? So the force on the top is going to be equal to the pressure at the surface times the area at the top surface. And there's going to be a larger, presumably, if you believe we'll show this in just a second, that the pressure is actually going up as you go down. So the pressure at depth h times A gives me the upward force from below, and it's going to be bigger if the pressure is actually going up as we go down. That's how I'm showing it. But in any case, you don't have to believe that. The sum of these 3 forces better be equal to 0, because a box of water sitting in water doesn't want to sink or float. It's neutrally buoyant. It neither wants to sink nor float. So the sum of the forces is 0 on it. So let me take plus y is up and do the sum of the force y components is 0. We've got one positive y component, that's the force upward on the bottom, P depth H times A, and 2 negative Y force components, right? And just setting those equal to 0, we can calculate P at depth H minus P at the surface. Just solving for that. P at depth H is equal to P at the surface plus rho GH. So that means the pressure at depth H is rho GH bigger than the pressure at the surface. Or when you go down by a depth H in a fluid, the pressure increases by rho GH. Okay, and that's our first. Everything we've talked about so far is a little bit, I don't know, we can't calculate with it. Here's something we can calculate with. So let's do an example problem. That's what this was about. It's not only, you don't have to be at the surface and go down. You could actually be down at a certain depth in the fluid and go down by, 1 meter, and you can calculate what the increase in pressure there is. You don't have to start from the surface to use that. Well, if we want to know what the pressure is, the absolute pressure is at some point in the fluid, we need to know what the pressure is here at sea level, just due to the atmosphere, right? Because the pressure is increasing as I go down in the fluid, but it started out non-zero out here. In fact, we have quite a high pressure in the room. We're just used to it, so we don't notice the extreme pressure around us. And then it starts increasing as we go down in the fluid. So what's the pressure around us? As we discussed, the pressure in the atmosphere is increasing as we go down. We're interested in the atmospheric pressure at the surface of Earth, which does vary a little bit, but it's pretty much constant. And we want to know it in the SI units, which remember is pascals. That's newtons per square meter. We can't use delta P equals rho GH since rho isn't constant here. So we can't calculate what the atmospheric pressure is in any easy way that we've talked about in Physics 110 so far. And that means that someone has to just experimentally measure it and see what the pressure is at the surface. And so here's the result. It's very close to 1 times 10 to the 5th, or 10,000 newtons per square meter, or 10,000 pascals, or sometimes we write it as 101.3 kilopascals, but close to 10,000 in SI units, or 10 to the 5th. That's the SI units. Because it's so convenient, those of you who have done some chemistry before, a convenient non-SI unit is atmospheres. An atmosphere is defined as the atmospheric pressure at sea level. So 1 atmosphere, that's not an SI unit, is the same thing as 101.3 kilopascals. It's just nice because you may not remember what the value is in pascals, but you are always assured that it's 1 atmosphere in these non-SI units. People will often state problems and say, well, the atmospheric pressure is just 1 atmosphere. Now, to measure this, you can't just use a tire pressure gauge or something like that, because pressure gauges, the kind we're used to using to pump up bike tires or car tires, they don't measure absolute pressure. They measure what's called gauge pressure. And gauge pressure is the pressure difference between the pressure at sea level and the pressure in what you're trying to measure. So when you pump up your, bike tires to so many pounds per square inch or something like that, that's not saying that's the absolute pressure. That's saying that's how many pounds per square inch of pressure you have above just the ambient pressure around us, which is actually quite large already. Okay, so if you want the absolute pressure, which is just plain old pressure, you have to add atmospheric pressure to the gauge pressure to get the absolute pressure. So if you know the gauge pressure in pascals, you just add this number in pascals onto it. Okay, so just maybe this is beating a dead horse here, but I had this picture from before that where here's the absolute pressure. It's pretty constant here in the room, right? It is going down a tiny bit as I go from the floor to the top of the room, but I really have to go up pretty far, hundreds of feet, thousands of feet. You'll definitely notice it. Your ears will be popping, but even hundreds of feet. When I'm coming here from Lexington, you go down over the bridge to go over the Kentucky River, and your ears sometimes pop there, and you're probably only going down like 100 feet or something like that. It's not too far down. So we're sensitive to that kind of thing. But if you're talking about a graduated cylinder, there's not much pressure difference in the atmosphere between the top if it's empty and the surface of the fluid. But once I get in the fluid, the absolute pressure goes up. If this is what it is in kilopascals, remember 101.3 is atmospheric pressure. To get the gauge pressure, we just have to subtract off 101.3. So the gauge pressure is 0 there and starts going up from there. Okay, here's an example problem. Then we'll do one on a worksheet in just a second. Here is, typical city kind of situation where you've got some water that's been pumped up into a water tower, and the top of the water in the water tower is open to the atmosphere. Maybe not just by having the top open, then you'd have a lot of evaporation, but at least it is open so that air from the atmosphere can go in there if it likes. So at the surface of the water in the water tower, we have atmospheric pressure. And the question is, what is that absolute pressure down here at the faucet, which is, if you follow the pipe, starting from the surface, you have to go down a net distance of 30 meters at the height of the faucet. I guess I should, mention that, it seems a little bit strange because we're squirreling our way through that pipe. But, if you have some water like this, or some kind of fluid, the pressure increases, we found out, as we go down, according to rho GH, rho of the fluid times G times H. So if I go down a distance H, pressure increases. Pressure isn't changing as we go along there. Then the pressure decreases as we go along there, not changing, increases, not changing, decreases. So I can follow water through a pipe. As long as the water's not moving, we're talking about a static situation. We don't expect there to be any sort of frictional forces. And so even if this is just water in a very thin pipe, we can follow it down and subtract. And what I really care about, if I am interested in the pressure at this point, is how far that is H. Oops, sorry, I'm used to quantum mechanics and writing H bars. H below the surface. So that's what we're concerned with in this problem here. How far below the surface of the water is the faucet? And we're told that distance is 30 meters. Okay, so to calculate the change in pressure first, and later on we're going to have to add on the atmospheric pressure, right? Change in pressure is equal to the pressure in the faucet, that's the higher pressure, minus the pressure at the top. I wrote that before as P atmospheric, but here it's written, just because I stole somebody else's picture, it's written as P0 here. The difference in pressure is equal to the density of the fluid times G times H, and our H is 30 meters here. So if I solve for P faucet, that's what we want, just by adding atmospheric pressure onto both sides. We get P faucet is atmospheric pressure times rho of water is 1,000 times 9.8 times H is 30, and we get 395,000 pascals. Notice, that's not particularly interesting, but it's quite a bit above what atmospheric pressure is. It's about 4 times what atmospheric pressure is. So notice that if you go here, we've gone down by 30 meters, and we've added on or increased by about 3 times atmospheric pressure. Atmospheric pressure is 100 kilopascals. We've increased by almost 300 kilopascals, and that means it's going up by 1 atmospheric pressure almost every 10 meters. So when you go down 10 meters in water, this is only true for water. It would be a smaller distance if we were in mercury, and it's a much bigger distance if you're in air. But for water, if you go down a depth of about 10 meters, it increases by 1 atmosphere. Go down another 10 meters, increases by another atmosphere, and so on. It's not that big of a distance. Okay, and notice that here, since we're calculating the absolute pressure at the faucet, this number right here is what we would call the gauge pressure, how much above atmospheric pressure that is. Okay, let's try a worksheet problem. For those of you who are on Zoom, I originally posted this under a week ago on Monday, date on the website. So here is something that, sort of a pain to create, but if you like to give your fish a fun place to play, you could fill up 2 aquaria and then have a little clear piece of tubing that's big and plenty big for the fish to get through. Fill it up with water and get it so that the ends are stuck under the surface of the 2 aquaria. And then your fish would be able to swim through the water bridge from one aquarium to the other. And here we're just interested in the pressure at various locations. The pressure at the bottom of the aquarium, pressure at the very top of the water bridge. The top of it is 12 centimeters above the surface of the aquarium. And then finally, what the gauge pressure is at the very top of the water bridge tube. So see if you can answer those. Maybe I should arrow back. You might want some of the numbers that are appearing on here. Atmospheric pressure is shown on there, and the density of water is 1,000 in SI units. You'll need that too. I guess I should say, just to be clear, whenever someone asks for pressure, by default, that means absolute pressure. We will say, at least in this physics class, gauge pressure if we mean the pressure above and beyond atmospheric pressure at sea level. Okay, here's my rough sketch of the aquarium situation. The bottoms were supposed to be equal, but they don't look quite equal there. And in A, we're asked, what is the pressure at the bottom of the aquarium? That's 0.2 meters below the surface. The surface, we're going to assume, is an atmospheric pressure. That can vary a little bit, but this is sort of the average value of atmospheric pressure. So the pressure at the bottom is equal to the pressure at the surface, which is 101.3 pascals. Pressure at the bottom is the pressure at the surface plus rho GH, where rho is the fluid we're talking about. Here it's an aquarium. We're talking about water. Water has rho of 1,000 times G is 9.8 times H is how far you're going in depth in SI units. That's 0.2 meters. And so calculating that all together in pascals, I get 1.033 times 10 to the 5th pascals. You know, it hasn't gone that much up from atmospheric pressure, not surprisingly. Remember, to go up by 1 atmosphere, you have to go down 10 meters. So it's not, you know, this is a very small 0.2 meters is not close to that. So it's going up by a small fraction. So that's P at the bottom. That's A. What's the pressure at the top of the water bridge? Well, here we're above, we know, so, you know, following a path here from the surface of the water, right? The pressure is atmospheric pressure there. It's increasing. Then it stays constant. Then it's decreasing. Now we're back at atmospheric pressure there. And it's still decreasing further as we go up to the surface there. The question is, what is it here compared to there? Well, it's going to be less, right? It's got to increase as I go down in the fluid. And therefore, it's got to decrease by rho GH as I go up in the fluid. And the H we're concerned with here compared to atmospheric pressure is it's 12 centimeters above a point where it's at atmospheric pressure. So I might write that as pressure at the top of the bridge is equal to atmospheric pressure minus, it's going down as you go up in the fluid, 1,000 times 9.8 times 0.12. Okay, on my solution, I have 1.00. Again, it's not that big of a difference from atmospheric pressure. 1.001 times 10 to the 5th Pascal, or 100.1 kilopascals. Question so far. Okay, the gauge pressure is by definition whatever the pressure is at the point you're measuring minus atmospheric pressure. Sorry, this is the pressure at the point we're measuring minus atmospheric pressure. And atmospheric pressure is greater than this pressure. So when we subtract them, we're actually going to get a negative gauge pressure. Most tire pressure gauges don't tend to ever have to measure something at a negative gauge pressure just because we don't use them that way. That's why they don't have a negative part of the scale. But there's no reason that a pressure gauge couldn't go positive and negative if you applied a suction, so to speak, to the one side. So the gauge pressure is just going to be this number minus this number, which is, I get minus 1176 pascals. Sorry, that's sort of at the bottom there, but hopefully you guys can see it. Okay, any questions on that? It's just playing around with the formula. Dylan?
So why did you subtract the two pressures from part B, but in part A you added them together?
I did that because this H, when we use the formula rho GH, the H means how far you're going down in the fluid. If you're going up in the fluid, H is negative. So I could have put this as a plus with a minus 0.12, or I just said, you know, it has to increase by that amount as I go down here. So it's got to decrease by that amount as I'm going up in the fluid. So I just subtracted off the same number. Either way. Other questions? There was an experiment that I just don't have quite set up that we could have looked at in the lab, which is the following related to this. I've got a long flexible but clear plastic tube. This was an experiment that when I was in graduate school, we used to do with the undergraduate physics classes. You know, sort of in the basement of a stairwell, get a big wide bin and fill it with water. And you take one of those flexible plastic clear hoses, maybe about a ½ inch inner diameter, and it's all fill the whole thing up with water, and it's all coiled down, you know, down in here, but the whole thing is filled with water, right? And it's coming up, filled with water. You let all the last bit of air out of the top, and then you can cap it with your thumb if you're strong enough, or you can put, you know, some sort of very strong cork in there or something like that to keep air from getting in. So you're capping it in there. And the other end is just sitting here open at the bottom, open to the fluid. And what you're going to do is keep this cap end capped with your thumb maybe, and you bring it out of the water and you start going up. And you're in a stairwell and you start walking up the stairs. Okay, first floor, second floor, third floor. And at some point up there, something very strange happens. Okay, you're watching it. You got the fluid in here. You're walking up, 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 up. And suddenly, as you're watching the fluid where your thumb is, something remarkable happens. Suddenly, at a certain point. Anybody have an idea what happens? No, it doesn't shoot out. I mean, I'm assuming you're strong enough to keep it, and the hose is strong enough to hold it in. And the hose is strong enough that it doesn't collapse or anything like that or explode. I'm going to carry it up. So let's suppose I carried it up, you know, so I've got the surface of the hose coming out. It's all filled with fluid, and I've carried it up. It's capped at the top, right? However I do that, right? So suppose I totally seal it off. No air can get in there. It's capped to the top. Here it's at atmospheric pressure. Here it's at greater than atmospheric pressure. But when I go through the tube, it's back at atmospheric pressure by the time I get to the surface in the tube, right? Right, it's gone up, then it's roughly constant, and then it goes back down to atmospheric pressure. Now it's less than atmospheric pressure, even less, even less, even less, even less. Yeah.
The whole tube be filled with water, like whenever you put your straw in the drink and put your tongue over it.
Well, it will be, yeah. So it will totally be filled with water, and that's probably shouldn't be surprising, or I'm imagining that's not surprising to you, right? You're carrying it up, it's filled with water. You're pulling this water-filled tube up. You've got it totally sealed off. Maybe we, you know, absolutely weld the thing together, melt the plastic so no air can get in there. You get up about 3 stories up, depends on how high the stories are, and all of a sudden, air appears at the top of the tube. And you start walking up, and the level of the water just stays constant. You can walk up several stories from there, and the level of the water will just stay constant. Where did the air come from? And then as you come back down, the level stays constant, and all of a sudden it's filled with water. It stays filled as you go down. Sorry, I'm sort of gesturing maybe to the side of the camera. I don't know if the same camera could see that, but it's quite remarkable, and it works really well. Except that, well, let me just explain what's going on, right? The pressure is going up. It's going down, down, down as you raise this up. Keeps getting smaller at the top because I'm raising it smaller and smaller. What's causing that fluid to stay up there? Well, you can think of it as there's pressure down from the atmosphere, which is pushing it and is causing it to go up to a certain height in the tube. And as long as the pressure is greater than 0, it keeps pushing the fluid up. But you can't have pressure that's less than absolute 0. So what happens is at some point, the pressure in the tube, you've gone up, you know, several stories, and you keep raising it up, and the fluid level just stays right there. Keep raising the tube up, and the fluid level just stays right there. This is the point at which the pressure has gone to 0 up there. What's causing this fluid from not falling down? Well, there's pressure that's holding it up from the bottom, is able to support the weight of the fluid up above it. But at some point, if the pressure is 0 here and you try to put some fluid on top of it, there's nothing to push, right? The whole force from the fluid below would be the pressure times the cross-sectional area. If there's 0 pressure right here, this fluid's just going to fall down to that level until the point where there's fluid below. So it's quite amazing. You raise it up, the fluid stays at the constant level. You raise it back, you pull it back down, and the fluid is essentially at the same level. The disappointing thing is there's always dissolved gases in water. And so unless you've bothered to get all of the dissolved gases out of it, some of the gases, when you get pretty close to a vacuum up here, some of the gases will come out of solution. And when you pull it back down, you might have like a centimeter of gas at the top of the tube. And then you go back to the bottom, you let that out. If you do that a few times, you'll get all the dissolved gases out of the tube. And it's quite amazing. I was going to set it up, but I just have the right. I tried to do it with stopper at the top and vacuum grease, but I was still getting air leaking in, because once you pull it up to the point where that fluid stays at the same level, that's pretty much a pure vacuum at the top. Now there's a little water vapor in there too, so it's not exactly a vacuum, right? When you get very low pressure, the water wants to boil or sort of evaporate out of there into the essentially what would have been a pure vacuum at the top, but it works remarkably well. So it's just another kind of thing that's like that water bridge. It's a very tall water bridge. Sometimes there's, you know, a classic physics problem in introductory physics textbooks is, suppose your neighbor wants to steal your water from your swimming pool. I don't know why anybody would do that. How tall do you have to make your wall so that they can't siphon your pool water out? I don't know. I've just seen it in several introductory physics textbooks. Same kind of thing. You got to make it taller than the point at which the pressure would go to zero, because once it goes to zero up there, doesn't matter how much you're quote unquote sucking on the other side, right? There's nothing below zero pressure. That means there's no more pushing from the bottom. And if you try to put some fluid on top of there, it immediately sinks down because there's nothing to hold that extra weight up above it. All right, that's rho GH. That's one of our calculational formulae, not too hard to work with. Here's a second thing that we can calculate with. Pascal's principle. Oh, I guess I brought this thing too. This is the same idea, right? If I've got this flask filled mostly with water. The pressure at the top of the flask is below what atmospheric pressure, right? It's just like being at the top of the tube. Now that we've done this problem, it's not that amazing sounding, but okay. Pascal's principle says if you have a confined fluid, so I've got some liquid in a bag or something like that, or in some system where it might be able to move, but there's a piston that can push on it or something like that. If you apply some external pressure to a confined fluid, then the pressure is going to increase at every point in the fluid by the same amount. That is to say, if I just had a cylinder of fluid right here, and I put a piston on top of it, and I push down on that piston, the pressure is going to go up by the same amount. I think I have a picture of this here. Yeah, so here's my same picture I keep recycling of a cylinder that's got some fluid in it, maybe water or something like that. The pressure is pretty constant up in the atmosphere, but then it starts increasing as we go down in the fluid. I'm going to put what I am imagining is some sort of like piston, so I can push down on the top of the fluid, and maybe it's sealed around the edges. There's a little rubber gasket there, kind of like in a syringe. And I apply a force down, and then those pressures inside the fluid are not going to be the same anymore. But the idea is, however much the pressure increased at this depth in the fluid, it's going to increase by the exact same amount at every other depth in the fluid. So if it goes up by 300 pascals at one point, it goes up at 300 pascals at every point in the fluid. Okay. We can make some nice machines out of that involving what are called hydraulics. Here is a situation. One nice thing about hydraulic fluid is that you can push in one location, and you can actually, change the direction at which that force is going to be applied by having it wander through some tubes. So if I push on this piston, it's going to tend to want to push this piston in to the right, and this piston is going to want to go to the left, because by increasing the pressure here, I'm going to increase the pressure here, and that pressure times this area gives me a bigger force on that, right? So that was just a piece of this picture that's supposed to be of disc brakes. So here's the disc in your car, right? You push on the pedal, that pushes the cylinder, the master cylinder, into the fluid. That increases the pressure in the fluid here. That therefore, by Pascal's principle, increases the pressure in the fluid here and here. That exerts a bigger force on this piston right there and pushes this, whatever your brake pads are made of, hopefully not asbestos anymore, but something like that, right? Something that can handle ceramics probably, increases the pressure. So it's useful for transferring forces in funky different directions without involving weird cables in sheaths, things like that. Here's a hydraulic lift. The idea is by applying fairly small forces, you can lift things that have great weights. So for example, if I've got a car on a lift, now don't take this picture too literally, there's not this much hydraulic fluid in a hydraulic lift. But imagine I've got a very small cross-sectional area over here and some sort of piston that I can push down with, right? And I've got a very large cross-sectional cylinder over here. They're calling that A out in the figure. And we've got the pressure here just underneath that. Now in this way it's drawn here, the height in the fluid, right? Whatever the pressure is here at the side over here, it increases from there as I go down in the fluid, then it stays constant, then it decreases. So the pressure right here is the same as the pressure right there. The pressure is the same. That doesn't mean the force is the same, because the force associated with the pressure is pressure times area. So let's do a little bit of a calculation associated with that. It's amazing that just by pushing with a very modest force on this side, you can get a huge force upward on this side. I might be able to push with 1 Newton on this side and be able to lift up 10,000 Newton weight on the other side. So here, again, the starting point for this is use the fact that the pressure here is equal to the pressure in the fluid over here. The pressure is changing, it's increasing as you go down, but then as you go up to the same height, the pressure is the same. The pressure is the force divided by the area. See what that means for the force on this side compared to the force on this side. So the question is, if we want to lift a car that has a weight of 10,000 Newtons, how hard do we have to push down on the piston on that side if the radii are 1 centimeter and 1 meter? Problem 2 in the worksheet. Okay, I'm noticing the time is sort of short now. It's 3:56. So let's just go through the solution quickly. There's not too much to it. The idea is here, maybe I should unshare this, but before I do that, notice that before I started pushing down, maybe it's very close to atmospheric pressure here, and it's very close to atmospheric pressure here because nobody's pushing on it. We don't have a car on this side, and I'm not pushing on this side. Pascal's principle comes in that when we put these forces on the two sides, the pressure increases to some huge amount here. It also increases to some huge amount over here. And that's the only point in which we're using Pascal's principle. The rest of it is just the definition of, or relationship between pressure and force. The pressure at the piston on the inside, that was the side we're pushing on, is equal to the pressure that is being pushed up on the cylinder on the outside. And that means the force on the inside divided by the area on the inside is the force on the outside divided by the area on the outside. And I can solve for the required force on the inside and put in the numbers. The area is, we were given the radii, so we can just do pi r squared. So the force on the inside is equal to the force on the outside, which we're told we want to be 10,000 newtons, times A in over A out. So that's A in is pi times that radius was 1 centimeter squared. I'm putting it all in SI units, although you don't really have to here, that would cancel out. Pi, let's see, here the radius on the car side was 1 meter squared. And the pi's cancel out. And notice that even though this is a huge number, we're going to multiply by something small, right? The denominator is 1 after I square 1, but the numerator is 1/100th. When I square it, I get 1/10,000th, which then cancels out the 10,000 and actually gives 1 Newton. So this is an idea of something that's called mechanical advantage in hydraulic systems, where by applying, it's sort of like using a long stick as a lever. By applying a very small force here, I can lift up something very heavy. It's the same way here, where applying a small force at one side, I can lift up something very heavy on the other side. Okay, let's stop it there.